When we think of serial communication, we think of protocols like USART, SPI, or I2C. This helps us transmit and receive data at high speeds. But as we all know, there is a well-known limitation, which is the transmission distance. The greater the transmission distance, the more distortion we have in the signal due to various factors, which we will delve into specifically in another video. While we have certain solutions, such as the RS232 interface for USART or a buffer driver for I2C, these have considerable limitations, especially with the communication speed. So, how can these protocols be transmitted over long distances? They use a different system called differential transmission. This system works by, as its name suggests, a differential system, that is, two opposing signals directed to a comparator. These signals are opposite in value, meaning that while signal 1 has one value, signal 2 has the opposite value. So the comparator does the following. When signal 1 is greater than signal 2, the output is 1, and in the opposite situation, it is 0. Why is this system used? What benefits could we obtain from doing this? Well, the trick is that the difference in these signals does not occur precisely in the absolute state values, like 3 volts or 0 volts, but occurs in specific calibrated values, such as 200 millivolts. What this causes is noise immunity, because no matter how much the signal deforms, this difference will continue to occur and we will be able to maintain excellent communication integrity. For this reason, high-speed communication systems use this method. There are different methods or variants of differential communication, such as LVDS and HVDS, but we will address those in another video. Today, we will focus on a hugely popular differential communication interface called RS485, using the MAX485 integrated circuit from Maxim Semiconductors. First, we need to understand the configurations of the interface. We basically have two, half duplex and full duplex. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In Prism Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. In half duplex, at any given time, we can only receive or transmit. In full duplex, we can send and receive data at the same time. Why implement one or another? It translates to our needs. If we don't need such fast communication, half duplex is more than enough. If we have an application where the required speed is higher, we will use full duplex. Remember that by using full duplex, we are using a larger integrated circuits, along with more components and more signal tracks or cables. Also, in both half and full duplex, we can have different masters and slaves connected to the same communication node, as happens in SPI. Well, now that this is clear, let's analyze the MAX485 integrated circuit. In this case, the model of the integrated circuit is configured only for half duplex communication. As we can see in the internal structure, the transmission and reception nodes are connected to the buffers. For this reason, we can perform half duplex communication. What characteristics do we have in the integrated circuit? Superficially, we see that the data rate is up to 2.5 megabits per second, which is approximately 212.5 kilobytes per second. It can operate from 5 volts to 12 volts. It requires a 27 ohm load and has short circuit protection for 250 milliamps to avoid damage. The interface capacity runs up to 4,000 feet in length, which equals to 1,219 meters, giving us a significant advantage over long distances. The datasheet indicates that it has ESD protection up to 15 kilovolts, which is usually the standard in interfaces intended for long distances or industrial purposes. This integrated circuit is available in various packages, such as PDIP, SO, Micromax, etc. So we have a variety based on the needs of our design. Now, let's look at an example of the signal. We can find that with the purple signal being channel A and the blue signal being channel B, since we have an embedded logic and above we have the decoded signal as start, H, and stop. This is an example done with the UART protocol, but how will it work with other protocols? In the RS485 interface, we have to use differential pairs for both communication and clock channels. In the case of UART, we do not have a clock signal, but in the protocols like SPI and I2C, we do have a clock signal. But for example, in SPI, with the chip select pins, it may or may not be necessary to use differential pairs, depending on the case. Now, we must consider the factor of data collision. Data collision occurs when we have a half duplex configuration, that is, transmission and reception on the same channel, or full duplex, a dedicated channel for both, where multiple masters or peripherals try to send data at the same time on a single channel. When we have a single master controlling peripherals, the risk of data collision is usually minimal or null. But when there are multiple masters, the risk can be present. Although integrated circuits have internal protections against data collision, we must be aware of this problem and coordinate well when communicating with multiple masters or peripherals. When we only have one master and peripherals, we need to measure well the times in which the peripherals process the instruction and return the data to avoid this collision problem. Well, now that we know the interface and have learned most important aspects, it is time to draw conclusions. When and why should we use the interface? The current configurations of RS485, whether in full or half duplex, give us enormous advantages in long-distance transmission or in the presence of much noise. When and why should we not use the interface? We should definitely not use the interface when the data rate is higher than specified by the integrated circuit in use. There will be occasions when we need data rates higher than 2 megabits per second, and here is where we will see the limitation of this interface. For cases where we need a much higher data rate, which is usually shorter distances, we must look at other interfaces. Well, in this video we saw a theoretical example of the interface operation and the datasheet analysis of an interface. In the second part, we will see the physical operation of the protocol and push an interface to its limits to verify its datasheet characteristics.